I'm Akhil. I'll be talking about conserved currents and fluctuations by holography. This work in collaboration with Jewel, Chandan, Loga, Mukund, and Sid. So this is an overview of the talk. We'll first run through some motivation for why the things we are doing, and then we'll talk about roughly currents and fluctuations. And then we'll give a lightning review of AdS CFT, and then a bit more specifically on the calculations we are doing, and then some future directions. So we have been in the business of studying open QFTs. These are typically coupled system and bath field theories, where the bath degrees of freedom are often either ignored, inaccessible to the experimentalist, or in a more calculational perspective, integrated out or averaged over. The observables in the theory are like system QFTs correlators. And so how does such a theory look? It's typically non-unitary, dissipative, and more we don't know because it's mostly understudied. And like even important questions like how does renormalization work in such theories is a surprisingly hard and subtle question. You can ask Chandan more about it, and you might even spot a tear in Chandan's eyes because it's that hard. That's a joke. What's a good non-trivial bath? We want a local open FT field theory. So we would want our bath to forget fast. That means the correlators of the bath decay fast, and so that we can do a Markovian approximation and get a local effective description of the open QFT. So you want to say, well, maybe if you want to consider thought of fancy bath, we can consider maybe a holographic CFT. It's strongly coupled, so it's forgetful. You can study it from the bulk side, and then there's a well-defined procedure to average out the CFT via AdS CFT. So current fluctuations, or some Johnson-Nyquist noise kind of phenomena. So like we all know that there's a thermal a resistor at a finite temperature has a fluctuation of currents or potential across it called the Johnson-Nyquist formula. And the equation, the first line which describes such a phenomena, looks very much like is a Langevin equation, and it looks very much like a Langevin equation for a Brownian particle, where like you replace the dissipation by resistor and mass by inductance and so on. And the right side is a stochastic potential seen by some ammeter trying to measure the current across this resistor. And there's a fluctuation dissipation relation which goes like that. It relates the temperature and the variance of this observed potential and the resistor by this fluctuation dissipation relation. Or alternately, you can think of them as thermal fluctuations in the potential measured across this resistor due to some noise currents to them. So can we derive such equations from first principle? Yes, we can. Like Langevin equation, we can derive from first principles. You can study the joint evolution of density matrix of some, say, an oscillator coupled to some larger set of baths, then integrate out the bath and look at the effective action for the evolution of this density matrix for the oscillator or some Brownian particle. And you can typically use Schunke-Keldysh formalism to do that, which is basically a doubled path integral setup for evolving the Ket and Bra vectors of the system separately, right? So our objective is to couple a gauge field to some charge current density operators in the CFT. So compare this with Maxwell theory, where you have currents and then gauge fields. You don't ask where the currents come from, but you really write equations thinking of the gauge field as your primary object. So then you average out the CFT, study the effective dynamics of probe gauge field. And then, so the gauge field here is the probe. You are probing some bath degrees of freedom and just looking at the gauge fields. And basically, we are staring at some flickering light from a ball of plasma. So then there's some quick dictionary for AdS CFT. So antidistant spacetime, a negatively curved spacetime. It pulls together things in it. It's basically like a solid cylinder. Objects and things living in the spacetime are basically going to think they are in a box. It has a time-like boundary, which is important for us because our CFT secretly lives there. Yeah. And the CFT conformal field theory, CFT, a conformal field theory, it's scale invariant. Roughly zooming in out is a symmetry in this theory, and it's also the thing which gave us trouble in the StatMech 2 course. Remember critical points and all the scaling dimensions and all that discussions. So the basic statement of the AdS CFT correspondence from a practical perspective is this. the log of CFT's generating functional for the moments of a particular, say, a collection of operators is roughly equal to the on-shell action of some dual field in the bulk AdS. In a more precise way, the object on the LHS, which is some generating functional for moments of operator O hat with some sourcing small phi, is equal to some partition function of some bulk field capital phi, where the capital phi is linked to the sourcing small phi by this relation, that the capital phi asymptotically approaches small phi. So the interesting thing about AdS CFT is that it's a strong weak duality. So it's a strongly coupled CFT, which is an imposter for some kind of perturbative gravity with small Newton's constant, and you can do perturbative field calculations there. Hence, it's holographic. CFT lives in one dimension lower. Recall the time-like boundary, and then quantum states in CFT are dual to geometry of the bulk. For example, a thermal ensemble of the CFT is dual to a black hole in an asymptotically AdS spacetime. And it's not any black hole. The black hole temperature of the black hole's Hawking temperature should match the CFT temperature we are looking at. And that's precisely our scenario. We'll study fields in black AdS geometry with a black hole, and evaluating on-shell actions of bulk fields in this background correspond to integrating out the thermal ensemble of CFT. But wait, we talked about doubling the path integral for CFT. We wanted to study the evolution of Ket and Brass separately, and that would need us to double the black hole geometry. How we do this is by studying the bulk fields in a slightly different geometry from what we are used to in textbooks of GR. We study two geometries, a Ket and Bra black holes, glued behind the future event horizons. So in very layman terms, that means if you are a Ket person and you run into the black hole, behind the horizon you would do a Bra version of yours doing the same. And a bit more about the specifics. So the fields dual to CFT currents are bulk gauge fields. The effective boundary gauge field action is same as the bulk on-shell action. So there is a bulk gauge field, there's a boundary gauge field. Boundary gauge fields from the CFT perspective were the sourcing in the CFT, and in the boundary perspective there was sourcing in the CFT, the boundary gauge fields, and then when you move into the bulk, they turn out to be some bulk gauge fields which take the boundary values as you go to the boundary. Right? Yeah. So there's a catch. The effective action is non-local for the boundary gauge fields. The effective action is non-local due to soft small omega k modes associated with current conservation, which shows up in your calculation as a failure of your derivative expansion for solutions. So basically what you're going to do is you have some Klein-Gordon kind of equations, or some field equations in the bulk, which are typically hard to solve. You have to resort to some kind of derivative expansion, which means you're going to think of your frequencies in the Fourier coefficients as some perturbations. You're going to Taylor expand in them. It's like the dipole approximation. You just think of them as small and then expand to few orders. But though you do that, once you match the boundary conditions, you're going to see that the solutions action and so on would have 1 by omega terms, which basically makes your perturbative expansion invalid. So these soft modes correspond to poles of the retarded Green's function describing diffusing charge density modes. That is, the boundary charge densities would diffuse via a diffusion equation like this. And if you're doing a small omega k expansion, it doesn't make sense to invert this operator because it's going to look like 1 by omega plus k square or something. In a real domain perspective, they do not decay over thermal timescale beta of the holographic CFT, rather over macroscopic timescales. And that would mean that all that we record of our CFT being forgetful and so on goes out of the window. So we can, there's a solution. The solution would be to keep these diffusion modes, or small omega and k, off shell and write down a local effective action including them. And our challenge as basically so our challenge would be to figure out how to make them off shell. Yeah. And keeping diffusion modes off shell correspond to keeping bulk Gauss constraints off shell. By Gauss constraints, I mean there are, unlike the usual Gauss constraints we talk in Maxwell theory, is just del I fi equal to 0, which will be something like a del mu f 0 mu equal to 0, or f del mu, f t mu equal to 0. But there's also a Gauss constraint where you think of some radial evolution of some data, and then you can have a radial Gauss constraint. So what we see is that to have a to keep the diffusion modes off shell and also get a consistent derivative expansion, you will have to not impose 2 of these equations in the bulk. So our pseudo on-shell solution will not satisfy these 2 equations. And there is more to the story we don't understand at this moment. It's still work in progress, and we are still, there are some clarifications there's something we need to figure out to complete this calculation, and that's it. And there's some future directions. You can extend this calculation for having a Maxwell-Chern-Simons theory in the bulk, that is adding another Chern-Simons terms in the bulk, say in the appropriate dimensions, and then you can talk about non-abelian gauge fields in the bulk, where the boundary also has non-abelian currents. And there's a generalization to gravity, where the bulk gravity, where like you think about gravitational waves and perturbations in the bulk, and in the boundary, from the boundary, those correspond to the fluctuations of energy momentum currents in the boundary. And yeah, that's it. Thank you.
Questions?
So in the so naive question. So in the caveat that you discussed, so what is the symmetry associated with the soft mode that you talk about, and how does it relate to the non-locality in the
Sorry, there's no symmetry. It's some current. There's a conservation current. There's a symmetry of that kind.
Yeah.
But
how does it relate to the non-locality?
Soft mode itself. Soft mode is just, I'm just calling the small omega small k thing the soft mode.
How does it relate to the non-locality?
Oh, because you're going to have a solution which looks like 1 by omega in the Fourier space, like in the derivative expansion. You're doing a series expansion for the solutions, thinking of in the Fourier space, thinking of the Fourier coefficients as some perturbative factor, and then you will see that when you match the boundary conditions, you're going to get a 1 by omega. But that's like a huge factor. You're thinking of omega as small numbers, and you want to expand around omega equal to 0. But
that way, okay.
Yeah, that's what I mean. Yeah. Thanks.
Okay, let us thank Akhil.